So with probability, the second big idea that we finished section 3.1 last time, so we'll continue with 3.2 through 3.4. Okay. So the first big thing to recognize here in probability is what we call the conditional probability and the multiplication rule. So what we mean by this, we'll look at a few examples, and I'm hoping that things would become clearer as we look at more examples, is that, okay, let me just get a pen here. All right. So what we are considering here is the case where the probability of a particular event changes or doesn't change based on the fact that something else has happened prior to it. Okay. So we'll talk about what we mean by conditional probability, what we mean by dependent and independent events, and then we'll talk about the multiplication rule, which is a crucial way of being able to calculate probabilities in general. Okay. All right. So let's talk about conditional probability. With conditional probability, right, we're talking about the probability of one particular event occurring. So we're talking about this particular event occurring given that another event has already happened, right? So if you think about the probability experiments, there might be many stages to it. Something happening prior affects what happens next or doesn't, right? So that's what we're considering. And the class of probability that we are considering is where the fact that something has happened before can alter the probability of what will happen next, right? So the notation here is fairly straightforward. So we write it as probability. So to read this is the probability of event B given A has happened, right? So that's how you read. This is the probability of event B given A, right? So this basically makes sure that we have a conditional probability. The probability of event B is now conditioned on the fact that this prior set of conditions have been met. Okay. So it seems like a bit here. So we'll take a look at an example, and I'm hoping that things become clear from there. So consider this situation here, right? You have a standard deck of cards, right? If anyone's not familiar with that, there's 52 cards in a standard deck, right? So there's 52 cards, four suits. So there's hearts, diamonds, spades, and clubs, and there's 13 cards in each suit, right? So there's 52 cards inside a deck, and we are considering the situation where two cards are selected in sequence, right? The crucial thing here is the fact that it's happening in sequence. One is happening after the other, right? You're not just drawing two cards both at the same time. You're drawing one card and then drawing the next. So it's happening in sequence. We want to find the probability that the second card is a queen given that the first card is a king and assume that the king is not replaced. So if you want to imagine what the situation is, you open up a fresh deck of cards, you basically pull out the first card, it's a king, you throw it away, and then you go back into the deck and pull out a second card, right? Given that this is the what has happened, we are asking the question, what is the probability that the second card that you pull out from the deck is a queen given that you already pulled out a king and the king was not replaced? Okay. So if you can imagine what the situation is, this is the first event. The first card is a king, and the king is not replaced. Right? The king in the deck is not replaced. So when I pull out a card, which happens to be a king, and I throw it away, I will not have 52 cards left because I've thrown one card away. Now I have only 51 cards to choose from when I go to pick the second card. Right? So when I go to pick the second card out of the deck, I have 51 cards left. Right? And I have four queens in the deck. So the probability that now that I can pick a queen, given that the first card is a king and was not replaced, is now the four queens over the possible cards that I could be picking up. So 51 is the size of the event sample space. So these are all the possible cards that could have been picked up, and only four of them satisfy the conditions of being a queen. Right. So the probability is basically the number of outcomes in the event space or the number of outcomes in the sample space. The number of outcomes which satisfy the conditions that the card is a queen. There's four queens, one of each suit, of the 51 cards which are left in the deck. Right? So clearly, this is a case where the fact that I picked a card out of the deck which happens to be king and I did not replace it has an effect on what happens next. Right? The probability that the second card is a queen is affected by the fact that the first card was a king and was not replaced. In this case, it would get 4 over 51. Right? So in general, if you think about what is the probability of just getting a queen, so let me see if I can write this way. So probability, the independent probability of getting a queen out of a standard deck would be 4, there's 4 queens over 52 cards. Okay? So there were 52 cards in the deck, and that would be the probability. Right? So if I think about what is the probability of just getting a queen out of the deck, if I started with the standard deck and nothing happened before it, I have 52 cards to choose from, of which 4 of them are queens. So the probability of getting a queen out of this deck is 4 over 52. Now the probability of getting a queen out of this deck, given that the first card was picked out was a king and it was not replaced, that means I threw away the card. Now the probability is different. Right? That's the crucial thing about understanding conditional probabilities, is that if something happens prior to whatever event it is that you're considering, that might alter what the probability itself is. Okay? All right. So let's see a couple more examples to really uh, drive this home point through. Okay, so we have data on this presence of this gene in children and that being correlated with higher normal IQs, right? So we have a basic sample of children. There's 102 children in the sample, and this is the split, right? So we want to find the probability that the child has high IQ. So let me see if I can switch. Um, okay, we want to find the probability that the child has high IQ given that the child has the gene, right? So we are conditioning the fact that we want to find the probability that a particular child from the sample has a high IQ given that the child has the gene, right? So consider what the story is. If I ask just the question, what is the probability that the child picked at random from the sample has high IQ? If I just wanted that, right? So if I look at the probability that the child has um, high IQ, so let me look at this H IQ. Okay, this is will be okay. So it says okay, there's 102 children in my sample, of whom, if I want to ask the question, how many of them have high IQ? If I look at the high IQ, there's 52 of them who have high IQ. Right? The probability here would be 52 over 102 if I didn't condition it on anything. There's no preset conditions. All I'm asking is what is the probability that a child picked at random from the sample has high IQ? So you say, okay, there's 102 children. That's the total possible number of children I could pick from. 52 of them satisfy the conditions of my event that they have high IQ. So the ratio of those two, the relative frequency, tells me what the probability that is of the child having high IQ. But that's not what we are asking here, right? We are asking the question, find the probability that the child has high IQ given we are conditioning it on the fact that the child has the gene present. So if you really think about it, we are only concerned about children who belong in this category, right? We are conditioning it on the fact that they have the gene present, which is to say we only care about this 72 children who have the gene present. Okay, that's what we see. So there's 72 children who have the gene. So now the sample space is altered, right? So what we have is, what we're considering is only these 72 children who happen to have the gene. Okay, of the 72 children who have the gene, of this group who have the gene present, 33 of them satisfy the conditions of having high IQ. So the probability that the child has high IQ, conditioned on the fact that the gene is present, is that how many people do have the gene present? That's the size of the sample space, 72, of which 33 have high IQ. Right? The relative frequency again is basically the probability. So the crucial thing to recognize is to figure out whether you're dealing with a situation where you're considering a situation with conditional probability or unconditional probability. Right? This is a case where the probability of being high IQ is conditioned on the fact that the gene is present. Right? So we are limiting our sample space in this way. Okay. All right. So that takes us to the next idea here about independent events. Right? And the intuition, right, before we get into the expressions here on the screen themselves, the intuition here is straightforward, right? We think that we say two events are independent right? We say B and A here, two events are independent. If the probability that B will happen, given that A has happened, is same as the probability that B will happen anyway. So the fact that A has happened prior doesn't affect the probability that B will happen next. Right? This is the idea of independence. So the fact that A has happened before doesn't really affect the probability of B happening next. So if the probability of B conditioned on A or probability of B given A, if it's equal to just the probability of B itself, then we say that A and B are basically independent events. If that's not the case, then the two events are dependent. Right? So that's in notational form, that's what it's saying. The probability that B will happen given A has happened is just equal to the probability that B will happen anyway. So A has no effect, doesn't alter the probability that B will happen next. So this is a case where these two events are said to be independent, right? And you can reframe it so the probability that A will happen given that B has already happened is just equal to the probability of A for independent events. Right. So let's take a couple of examples to see how this works in practice. So we let's go back to the original situation, right? So we are selecting a king from a standard deck, not replacing it, and then selecting a queen from the deck. So event A is selecting a king from a standard deck and not replacing it. Event B is then selecting a queen from the deck. Okay. So let me consider the two probabilities. What is the probability of B given A? What is the probability that the second card is a queen given that the first card is a king? So this is a case where we already figured out that, okay, if I pick a card from the deck and it's a king and I don't replace it, when I go to pick the second card, I have only 51 cards left in the deck because I threw one of them out. I have only 51 cards to choose from. I started with 52. I picked the first card. It was a king. I threw it out. I have only 51 cards to choose from. And there's still 4 queens left in the deck. But now this tells me that the probability that the second card is a queen, given that the first card is a king and not replaced, is 4 over 50. Okay. If I look at just the probability of drawing a queen, right, the probability of B itself, selecting a queen from the deck, that's what I'm defining as B. If I think about what the probability of event B itself is, this is the unconditional probability. What is basically asking the question, what is the probability of drawing a queen from a standard deck? The standard deck has all 52 cards intact. There's 4 queens inside the standard deck, so the probability of drawing a queen from this kind of a deck is basically 4 over 52. So if I compare this to this, right, the probability that I get a queen in this situation is different than the probability of just getting a queen when nothing has happened prior. The fact that event A has occurred before it, right? The fact that there was something which happened prior to it, that the first card was drawn, it was a king, it was not replaced, alters what happens next. Okay? So this is a case where the probability of B given A is not the same as the probability of B itself. So this is a case where these two events are said to be dependent. So the fact that A happens prior to B affects the probability that B will happen next. Okay. So this is a classic case where the two events are dependent. The fact that one event has happened prior alters the probability of the next event. Okay. So let's consider a second example, and this should be similar. Okay. So we're going to do a two-part experiment. The first part, we toss a coin. The first part of the experiment is tossing a coin. We want to ask the question, what is the probability that if I toss a coin, what is the probability I get a head? And then if I roll a die, what is the probability of getting a 6? Right? And if these two events are dependent or independent. Intuitively, straight away you can imagine that these two events should be independent. In a certain sense, tossing a coin doesn't in any way affect what will happen on the roll of the die. Right? Both of these two things should be basically the same. Right. So that's what we find, right? What is the probability of rolling a 6 on a die given that I got a heads on a coin, right? If I toss a coin and get a head, that doesn't really the probability of rolling a 6 on a die. There's 6 possible outcomes that can happen when I roll a die. Only one of them is a 6. So the probability of rolling a 6 on a die is 1 over 6. Right? So this is probability of rolling a 6 is the same as the probability of rolling a 6 given that I got a head on a coin. These two events don't affect each other, right? So there's a classic case where the probability of B given A is the same as the probability of B. This is the case where these two numbers basically are the same and the two events are said to be independent, right? So that's the crucial understanding here, right? If if one event affects the probability of another event happening, then the two events are dependent. If if one event happens and it doesn't affect the probability of what will happen in B, then the two events are independent. Right? All right. So, which leads nicely into a fundamental idea in probability theory about the multiplication rule. Okay. So the multiplication rule basically says, ask the question: if there's two events that will occur, what is the probability that they occur in this sequence? Right. The probability of A. And the crucial thing here is this AND operator, right? The way to read this is that what is the probability that A will happen and then B happens, okay? So as you can imagine, if you intuitively, what the formula says is that that should be just the probability that A will happen. So A happens first. So what is the probability that A will happen? Times the probability that B will now happen given that A has already happened. So intuitively, it makes complete logical sense that this is the way to express this thing. So the probability that two events A and B will occur in sequence is the probability of A and B in sequence is the probability that A will happen anyway, because that's what happens first, times the probability that B will now happen given that A has already happened. So for independent events, the probability of B given A is the same as the probability of B. For independent events, you can verify that two events are independent by checking whether the probability of A and B is equal to the probability of A times the probability of B. Okay. So this is easily extendable to any number of independent events. It just keeps multiplying out. So if I ask what is the probability of A and B and C, and if all three events are independent, then that's just the probability of A times the probability of B times the probability of C, and you can keep going that way. Right? Okay, again, to fix ideas, let's go back to our examples and see how this gets operationalized. Okay, so the situation is again straightforward. Two cards are selected without replacing the first card from a standard deck. Right, that's the situation you're faced with. There's a standard deck of cards. Again, remember, in a standard deck, there's 52 cards, and then you're going to do two selections. You're going to choose two cards, one after the other. Right, you pick up the first card. You don't replace it. You basically pick it up and then throw it away. You look at it and then you throw it away, and then you go into the deck and pick up the second card. We are asking the question, find the probability of selecting a king, and then the crucial wording is here, and then selecting a queen. Okay, so that's the question. So what is the probability that the first card is a king and the second card is a queen? So intuitively, if you think through the situation, that should be okay. Prior to picking the king, it's a standard deck. It's I've not changed anything. Nothing has happened before then. So that should just be the probability that I pick a king times the probability that I pick a queen given that I chose a king and did not replace it, right? The crucial thing is that it's happening without replacement. Okay, so if I think about the probability of getting a king from a standard deck, when I go to pick the king, there's all 52 cards still left in the deck, all 4 kings still left in the deck. So that the probability of the king is basically 4 over 52. Right? All 52 cards are still left in the deck, 4 kings left in the deck. The probability of getting a king out of this deck is 4 over 52. Times the probability of getting a queen from this deck, given that the first card was a king and was not replaced. Here the crucial thing is not about what card was drawn first, but about the fact that it was not replaced. So when I go to draw the queen, I have only 51 cards to choose from because I already picked one and threw it out. So I have 51 cards to choose from, 4 of them are queens. So the probability of getting a queen when the first card was a king and not replaced is 4 over 51. So the probability of doing these two events in the sequence where I first draw a king and then a queen is basically 4 over 52 times 4 over 51 or 16 over 2652, and so that's the probability. So this is the classic case of using the multiplication rule. So don't worry about memorizing these things. In a certain sense, it's completely logical. So if I ask the question, what is the probability of choosing a king and then a queen? It's basically saying what is the probability of getting a king times the probability of choosing a queen given that the first card that was chosen was a king. Given that this has already happened, what is the probability of not choosing a queen. Okay, right. So let's look at a second example, and I'm hoping that this will fix ideas even further. So a coin is tossed and a die is rolled. Again, there's a two-part thing, right? There's two events which are going to happen. First, a coin is tossed and the die is rolled, and we want to ask the question: find the probability of getting a head and then rolling a six. Excuse me, right? So the probability of heads on the coin toss and a six on the roll of the die. That's the crucial thing. The crucial thing here is recognize that it's an and operator between these two events. And essentially is suggesting that these two events need to happen in sequence. Right. Right. So if you look at the situation, what is the probability of getting a head on the coin toss and then rolling a six on the die? Right. The probability of getting this basically the probability of getting a head on the coin toss times the probability of rolling a six given that uh, a head was showed up on the coin toss. But the probability of a six that shows up on a roll of a die has nothing to do with what happened prior to it, what happened with the coin toss in general. So these two events are independent. So there's just basically the probability of getting a head on a coin toss times the probabilities of rolling a six on a die. So probability of heads on a coin toss. So one of two things can happen, a head or a tail. So there's two outcomes. Only one of them satisfies the conditions of my event. So the probability here is 1/2. And when I roll a die, there's six possible numbers which can show up. Only one of them is a six, so the probability of rolling a six is 1/6. So the probability of tossing a coin and getting a head and then rolling a die and getting a six is 1/2 times 1/6 or 1/12. Right? So this is a case where the two events are independent. Okay, so I hope this is clear. If there's any questions, ask in the comments once the video is uploaded, and I'll be happy to troubleshoot any issues which might show up here. All right, so let's take a more interesting example. Okay, so again we're going to try and use the multiplication rule. Okay, so the probability that a particular knee surgery is successful is 0.85. So they've collected some data and they find that about 85% of knee surgeries are successful. And we want to find the probability that three knee surgeries are successful. So it's basically asking the question, what is the probability that the first surgery is successful and the second surgery is successful and the third surgery is successful, right? So if you think about this, what happens on any of these surgeries is independent on whatever happens before it, right? A particular surgery is a particularly new set of circumstances. You can make a plausible argument that the events themselves are independent. What is the probability of success on one surgery has nothing to do with what happened before. So in a certain sense, the probability of each surgery being successful is 0.85, and they're independent events, right? So the chance of success for one surgery doesn't affect what the chance of surgery on success on the next surgery is, right? So what is the probability that all three surgeries are successful? It's the probability that the first one is successful times the probability that the second one is successful times the probability that the third one is successful, right? So the probability that the first one is successful is 0.85. The probability that the second one is successful is also 0.85. And the probability that the third surgery is successful is 0.85. So for three surgeries to be successful, it's basically, if you break it down, is that what is the probability that the first one is successful and the probability that the second one is successful and the probability that the third one is successful. So it's all operated by and. It's happening in a sequence. So the right operator here is and. Okay. So the probability that all three surgeries are successful is about 61.4%. Okay. All right. Hope this is clear. So let's move on and take a look at a different situation. Find the probability that none of the three surgeries is successful. Okay. So in a way, it's asking the question, what is the probability that the first one is a failure times the probability and the second one is a failure, and then the third one is a failure, right? Because the probability of success for one surgery is 0.85. So if 85% of the time the surgery is successful, the rest of the time the probability of failure for one surgery is 15%, right? So 85% of the time the surgery is successful, which means 15% of the time the surgery is successful if it's a failure. So the probability that none of the three surgeries is successful is basically asking the question, what is the probability that the first surgery is a failure, and the second surgery is a failure, and the third surgery is a failure? The probability that the first one is a failure is 15%, 0.15, times the probability that the second one is a failure is 0.15, times the probability that the third one is a failure is 0.15. The fact that the first one is a failure doesn't affect what happens on the next one and doesn't affect what happens on the third one. So these three events are independent, so you can just multiply them out this way, right? So there is about a 0.3% chance that all three surgeries in sequence are failures, right? None of the three surgeries is successful is a way of saying what is the probability that all three are failures. Okay. The last case that I want to consider in this is to look at the situation with at least one. Okay. So if I think about at least one, it, at least is always greater than or equal, right? I'm looking for the fact what is the probability that at least one of these knee surgeries is successful. Right? Okay, the opposite of at least one, if I think about it, right? So at least one means one or more. The complement or the not or the opposite of this is that of at least one is successful is that none are successful. Right? The opposite of at least one is none, right? If you're saying greater than or equal to one, that means the opposite of it is none. So I'm asking the question, what is the probability that none of them are successful, right? So you can use the complement rule, right? We already talked about the last class. So in section 3.1, what is the probability that at least one is successful is 1 minus the probability of its opposite or its complement, right? So the probability that at least one is successful is 1 minus the probability that none are successful. Okay. We already calculated what the probability that none are successful is. There's a probability that all three are failures. In the earlier case, we calculated that this was 0.003. So the probability that at least one of these three surgeries is successful is 0.997. Right? So here we're combining two key elements. We're talking about the complement rule, right? You'll be using the complement rule, and we calculated this probability by using the multiplication rule, right? The 0.03, which we calculated from the previous case, was an application of the multiplication rule that we have. Okay. All right. Hopefully that's clear. And again, if there's any questions, write in the comments, and then we can. I'll try to address them as quickly as I can. All right. Okay. All right. Here's one more example. Right. So let's just take a look at this one as well. Okay. So we have some data from the NRMP, so the National Resident Matching Program for medical programs. So this is how matching is done. So more than 15,000 US medical school seniors applied to residency programs in 2009, right? Data from 2009. Of those who applied, 93% were matched to a residency position. Okay. So of the 15,000 people who applied, 93% were matched into a residency position. 82% of the seniors who were matched into a residency position, so it's conditioned on the fact that you're already matched into a residency position, were then matched to one of their top two choices. Okay, so we want to know what we have a situation where we want to find the probability that a randomly selected senior was matched a residency position. First of all, that they matched into a residency position, and it was one of their top two choices. Okay. So again, crucially remember, whenever you see and, the two events need to happen in sequence, which is to say you're going to use the multiplication rule. All right. Event A is just being matched into a residency position. Event B is being matched to one of your top two choices, right? We are asking, if you think about what the information is, the probability of getting matched into a residency position is 0.93, right? 93% of everyone who applied was matched into their residency position. So this is 0.93, okay? The probability that you get one of your top two choices, given that you've already been chosen, is 82%, right? So this is the probability that you get one of the top two choices that you chose, condition on the fact that you've already been matched into some kind of residency. Of all the people who got matched into a residency position, 82% of them get matched into one of their top two choices. So if I think about the probability of A and B here, the probability that you're matched into a residency position and it was one of your top two choices, is the probability of A and B, which is the probability of A, the probability that you match into a residency position, times the probability that you get one of your top two choices, given that you've been matched into a residency position, right? So the probability of A here is 0.93. We already calculated that. The probability of B given A is 0.82. So the probability of A and B is 0.93 times 0.82 or 0.763. Okay. So a direct application of the multiplication. Second uh, example, that second situation, again, this is using both the multiplication rule, or basically we're trying to use a complement rule. Find the probability that a randomly selected senior that was matched to a residency position. So A essentially says, okay, they matched. So the condition is that they matched to a residency position, did not get matched with one of their seniors' top two choices. So if B is getting matched into one of your top two choices, as we alluded to here, then there's basically not B. Right? We are asking the question, what is the probability that you don't get matched into one of your top two choices, given that you are matching into a residency position to begin with? So probability of B complement given A is 1 minus the probability of B given A. This is basically the complement rule. We know what is the probability of B given A, it's 0.82 here. So 1 minus 0.82 is 0.18, and that's 18%. Okay. All right. So that basically covers the uh, section 3.2, right? It basically talks about conditional probabilities, in the sense that we found the probability of an event given that something else has happened. We determine how to distinguish between independent and dependent events, right? And then we applied the multiplication rule to find some probabilities. Okay. All right. Let's go on and talk about the addition rule. Okay. So we've considered the situation where two events happen in sequence. So the key thing was and. When we're talking about the addition rule, we're talking about two events, one of which could happen, right? So let's talk about this. Before we get into it, let's talk about this one key idea. This comes from set theory about mutually exclusive events, right? So if this is all the outcomes which belong in set A, and if this is all outcomes which belong in set B, this is a case where there is no common outcomes between A and B. There is no what we call intersection between A and B, right? So these are two events where there's no common point between, there's nothing in common between these two events, no outcomes which are shared between the two events. We call these two events mutually exclusive, okay? If you consider this particular diagram, this is event A, right? This is event B, but if you think about what's in between here, this is an intersection, right? There are some outcomes which belong both as part of A, but also as part of B, right? This is basically a case where the two events are said to be not mutually exclusive, because they have some outcomes where there exists a non-null or non-empty set of outcomes which satisfy the conditions of both event A and event B at the same time. Okay, what does this mean? So let's look at examples again, and hopefully that fixes ideas quickly. Okay, event A is rolling a 3 on a die. Event B is rolling a 4 on a die. Okay, so event B is rolling a 3 on a die, and event B is rolling a 4 on a die. Right? So if I think about it, the only outcome when I roll a die, there's 6 possible things. The only thing that can show up which satisfies the conditions of this event is if I see a 3. This is a 3. The only way I can satisfy the conditions of event B is if I roll a 4. Okay. So the first event has only one outcome, a 3. The second event has only one outcome, a 4. There is no common outcome between the two events. There's nothing which can show up on the die where I can say both event A or event B has happened. I can't say that both of them have happened at the same time. So these two outcomes cannot occur at the same time, and the events are mutually exclusive. If one happens, the other can't happen. If this happens, that can't happen. Both of them can't happen at the same time. That's a way of uh, maybe not fully describing what mutually exclusive means. Right? Okay, so that's a situation where the two events are mutually exclusive. So let's consider a couple of other situations. All right, event A is randomly selecting a male student. Event B is randomly selecting a nursing major. Okay, and the question is, are these events mutually exclusive? Right. So for event A and event B to be mutually exclusive, if this happens, this can't happen. If this happens, that can't happen. So for both the events to be satisfied at the same time, I need to randomly select a student who's male, but is also a nursing major. And so that can be done, right? The student can be, you can find a student who is a male nursing major, and this male nursing major is going to satisfy the conditions of both events. It satisfies the conditions of event A, the fact that the student is male, but it also satisfies the conditions of event B at the same time, the fact that they're a nursing major. So these two events are not mutually exclusive. Both of these events can happen at the same time, right? We can say that the two events happen at the same time. Which leads us nicely into what we call the addition rule. It says what is the probability of A or B, right? The crucial operator here is what is the probability that either A will happen or B will happen, right? So that's just the probability of A plus the probability that B will happen. Is A or B, they don't have to happen in sequence, one can happen over the other, minus the probability of A and B, right? Minus the probability of A and B. Okay. So to understand where this comes from, let's go back to the original picture. So if I think about these two events which are not mutually exclusive, right? So when I consider the probability of A, I consider all the outcomes which are in this circle here, right? So I count that common intersection between the two events once then. When I consider probability of B, I take into account all the outcomes which are in B. Okay. So if I think about it, this common point between A and B is getting counted twice. Once as part of A, once as part of B, right? So it's getting counted once as part of A and once as part of B. So that we are counting this region of intersection of A and B twice. So when we go into the formula, that's where it comes from, right? So to avoid double counting, we subtract the probability of A and B once because A and B is both part of A and part of B. So if I do probability of A plus the probability of B, I get the intersection twice between those. I need to only count it once, so I subtract minus the probability of A and B from. Okay. So, and if the two events are mutually exclusive, there is no intersection, so the probability of A and B is 0 because there is nothing like an intersection between these two events. So this is always going to be 0, and so the probability of A or B is the probability of A plus the probability of B. Again, this can be extended to any number of mutually exclusive events. Okay. All right, so let's look at a example. Again, I really hope the examples fix ideas firmly here. So you select a card from a standard deck. Okay, find the probability that the card is a 4 or an ace. Right. So what is the probability that the card is a 4, that the random card that you chose is a 4 or it's an ace. The crucial thing here is recognize that it's an or. Okay. The two events are mutually exclusive. So if I visualize this, the entire sample space is the deck of 52 cards. That's the sample space. The deck of 52 cards represents the big rectangle here. If I consider what cards satisfy the conditions for event A, there's 4 cards. Okay, right? One from each suit. There's 4 fours in the deck, and that's what satisfy the conditions of event A. So this is the event space. So if I consider the ace, right? There's 4 aces in the deck. That's what satisfies the conditions for event B. There is no intersection between these two events, right? We can't never find a card which is both a 4 and an ace, right? So these two events are mutually exclusive, and if you look at the diagram, it shows that there is no common intersection between those two. Okay, so the probability of getting an ace 4 or an ace is the probability of getting a 4 or plus the probability of getting an ace minus the probability of getting a 4 and an ace. That can never happen, so that's 0. So it's just probability of 4 plus the probability of an ace. The probability of getting a 4 out of a standard deck is 52. 52 cards to choose from, 4 of them are 4s. Probability of getting an ace from a standard deck is 52 cards to choose from, 4 of them are an ace. So it's 4 over 52 plus 4 over 52 or 8 over 52. Okay? So this is a case where the two events are mutually exclusive, so we don't have an issue here. Okay. Here's a second example where the events are not mutually exclusive. Right? You roll a die. Find the probability of rolling a number less than 3 or rolling an odd number. Okay. So consider the outcomes which belong in each event. Rolling a number less than 3. Less than means anything which is lower than 3 but not 3 itself, right? So if I think about less than 3, the two outcomes which satisfy the conditions of that is 1 and 2, right? So this is less than 3. If I consider the other event, rolling an odd number, there's 3 numbers which satisfy it: 1, 3, and 5, right? So odd, there's 3 odd numbers between 1 and 6, 1, 3, and 5. Okay? So if I think about, if a 1 shows up, if I roll a die and a 1 shows up, this is a case where I can say both events have happened simultaneously, because first I've rolled a number less than 3, that's the condition for that event, and I've also rolled a odd number, which means that if I roll a 1, both events can happen simultaneously. So this is a case where the two events are not mutually exclusive, right? There is one outcome which satisfies the conditions of both events. Okay, so we can go ahead and calculate the probability of less than 3 or odd, right? Or essentially tells me that the right rule for me to apply here is the addition rule. Okay, so the probability that the card is less than 3, okay, so there's 6 possible outcomes. 2 of them satisfy the conditions of that event, so that's 2 over 6. Okay. The probability of getting an odd number, 6 possible numbers that can show up, 3 of them are odd, so 3 over 6, minus the probability that I roll a number which is both less than 3 and odd, which is the case of 1 over 6. Right? So here's the case where I have the addition rule. The probability of less than 3 or odd is probability of less than 3 plus the probability of rolling an odd number minus the probability that the number is both less than 3 and odd at the same time. So the addition rule basically is applied and we get to the answer. All right. Okay. Hopefully that's clear. Hopefully there's no confusions there. Okay. Okay. Here's another example, right? So we have a frequency histogram on sales figures, sales volume. So it tells us for each range how many months there were when sales were made in that range, right, for the past 3 years. If the sales pattern continues, what is the probability that the sales representative will sell between $75,000 and $124,999? Okay. So what is the probability that, given that this is the pattern that's being exhibited in the data, what is the probability that the salesperson, you can realize sales between 75,000 and 124,199? So A is monthly sales. So I can split it up into 2 sequence of events. One is that I can make sales in this range, or I can make sales in this range, right? If I'm in either of these 2 boxes, I can say that I made sales between 75 to 124,999, right? This or this will satisfy the conditions of my event. So A is monthly sales being in this box, so this is my A and this is my B. Okay, so A and B are mutually exclusive. I can never have sales where I am both in this range and in this range because the cutoffs are correct. Right? I can't ever really have sales of both 99,999 and 100,000 at the same time. So there's no way I can have both of these events happen simultaneously. So the two events are said to be mutually exclusive. So the probability of A or B in this case is just the probability of A, the probability of being in this box, plus the probability of being in this box. So if I count up the total number of months, that's 36 months, of which 7 months I'm here, 9 months I'm here. So that's 7 over 36, that the probability that I'm here, plus 9 over 36, which is the probability I'm in this box. So that's 16 over 36. Okay. All right. So let's take a look at one last example, a little bit more involved example. So I hope that really fixes ideas here around the addition rule. So a blood bank catalogs the types of blood given by donors, right? A donor is selected at random. Find the probability that the donor has type O or type A. Okay. What is the probability that the donor has type O or type A? So we are asking the question, what is the probability that the donor is in this box or the donor is in this box of this type or this type? If you think about that, there is no common thing between these two boxes, right? Either a person has type O blood or type A blood, but you can't have type O and type A at the same time. The two events are mutually exclusive. Right? What is the probability of type O or type A? Is the probability that the person has type O blood plus the probability that the person has type A blood minus the probability that they have type O and type A, which is 0, right? So probability that you have type O blood is that, okay, so 409 different samples to choose from, right? That's the total number of samples. 184 of them are type O. So the probability that you can get type O blood is 184 over 409. Plus the probability of getting type A is of the 409 samples, 164 are type A. So the probability there is 164 over 409. So the probability of type O or type A is 184 over 409 plus 164 over 409. So that's 348 over 409. Okay. All right. This is a more involved situation. I think this would really fix ideas. Find a probability that the donor has type B or is Rh negative. Okay. All right. So consider the situation. You can be type B or you're Rh negative. The two events are not mutually exclusive because there is a common thing between them. You can be both type B, you can still have type B blood and still be Rh negative. So 8 of my people in my sample satisfy the conditions of both events at the same time. They're both type B and Rh negative. These two events are not mutually exclusive. Right? So type B or type Rh negative. So again, remember we're using the addition rule every time we see an OR. So we are asking the question, what is the probability of type B or Rh negative? And the probability of type B plus our probability of Rh negative. So the probability of type B plus the probability that you're Rh negative minus the probability that you're both type B and Rh negative. Type B, okay, so there is 45 people out of the 409 who are type B. So that's the probability of type B. Probability of Rh negative, so if you think about Rh negative, there's 65 Rh negative of the 409, so that's 65 over 409, minus the probability of type B and Rh negative, which is 8 over 409, right? This is minus 8 over 409, and so that tells me that the probability there is 102 over 409. Okay, all right. That's the end of section 3.3. So I'm going to end this video here, and then next week's video I'll